All right, so this is a lesson on hybridization. And today we're going to study how covalent bonds can be formed in the context of electrons and orbitals. Okay, so when we learn Bohr-Rutherford diagrams, it is quite easy to represent covalent bonds. All we have to do is just overlap the valence shell, and the electrons are found in the orbits between the two atoms. But then we learn that orbits do not exist. Instead, we have orbitals. So how does that work? So how can you have a covalent bond with orbitals? So we're going to learn about hybrid orbitals. We're going to learn the process of hybridization. And finally, two new type of bonds, sigma and pi bonds. All right, so let's do a little review on orbitals first. So if you remember, orbitals are regions of space around a nucleus where you have a greater than 90% probability of finding an electron. Okay, so it's a region of space. And there are different types of orbitals. They come in different shapes and sizes. Figure A is an s orbital. It's spherical. And B, you would have a p orbital. And p orbitals have two lobes. It is shaped like a dumbbell, okay? That two lobes means the same orbital. And you can have different orientations of that p orbital. It can be found along the z-axis or the x-axis or the y-axis in a three-dimensional Cartesian plane. Well, I shouldn't say plane, a three-dimensional grid. And then the d orbitals have four lobes. Okay, all of those lobes belong to the same orbital. We're not going to concern ourselves much with the d orbital today. Mainly, we will focus on the s and the p orbitals. And figure D to the right, you can see a combination of 1s, 2s, and 2p orbitals. If you just combine all of them together, you get that messy blob. Okay, so those are the superpositions of all of these orbitals together. All right, so how do we make bonds? Well, first we have to learn the valence bond theory. And this simply says that to make a bond, the orbitals of the atoms will overlap with each other. So if you have two orbitals, they will come together and overlap. And you form a new orbital, and you would have two electrons in that orbital, and they will have opposite spins. So this is illustrated by the picture, the figure on the bottom. You have two separate hydrogen atoms. Okay, they both have one electron each, so they all have an up spin. So when they try to make a bond to form H2, those two orbitals will come closer and they will overlap and they will form a single orbital. Okay, that would be the single overlap s orbital. And the spins of the electrons, one of them will be reversed because you must have opposite spins to be in the same orbital, so the up spin becomes the down spin. And that's how you have a covalent bond between two hydrogens. Okay, the red dots in the figure, those are nuclei. That's not an electron. So the electrons are likely to be found between the nuclei of the two atoms. All right, so do we have any questions regarding overlapping s orbitals before we move on? Okay, this one is quite simple. You don't have to just have s. Now, fluorine has two p orbitals, and fluorine needs one more electron. So one of the two p orbitals in fluorine is missing an electron. So that's the orbital that fluorine will try to bond with. What happens when H tries to bond with F? Well, the s orbital from the hydrogen will overlap with the p orbital from the fluorine. And when they do, if you just take a look at the picture on the bottom, they will merge into a bigger orbital, and it only merges with one of the lobes. Okay, and that lobe will become a lot bigger than the other one because you have a higher probability of finding the electron between the nuclei as opposed to somewhere else. Okay, so this will form a hybrid sp orbital. It's an overlapping orbital. Okay, does that make sense? All right, and same thing, the spins of the electrons will become opposite of each other. They both had up spins, but once they overlap, one of those electrons become a downspin. So those are really simple. Just overlap the orbitals. You can have an SS overlap, or you can have an SP overlap. You can even have a PP overlap. Now, the next one, let's look at something more complicated like oxygen. Now, oxygen has 2 half-filled p orbitals. It needs 2 additional electrons instead of 1. So both of those orbitals will be in a bond. Now, how would that work? Well, here's the electron configuration of oxygen. You can see that in the 2p. 2 of those are missing an electron. So instead, they will attempt to bond with an s orbital of, let's say, hydrogen. I'm using water as an example here. So what happens is that 2 s orbitals from 2 hydrogen atoms, they will bond with the 2 half-empty p orbitals. And we learned that the p orbitals are 90 degrees from each other. Okay, one on the z-axis, one on the x, and one on the y. So they're all 90 degrees from each other. So this would suggest that if you were to bond, water should have a bond angle of 90 because of the perpendicular p orbitals, as the picture will suggest, right? And they will overlap. One lobe becomes much bigger than the other lobe, and you would have the picture on the bottom right. But the problem is when we actually measure the bond angle of water, it's 105, not 90 degrees. That means this model is inaccurate. So we need to improve this model. So what happens? What can we possibly change so that water will not have 90 degrees? It will instead have 105. Well, that's when orbital hybridization comes in. Okay, let's take carbon, for example. So to illustrate orbital hybridization, you have to visualize electrons jumping from one orbital to another. So here's carbon. Okay, that's the configuration. 1s2, 2s2, and 2p2. Y'all know that carbon can make 4 bonds. Carbon has 4 valence electrons, and all they've got to do is find a partner. So now you would have 8 valence electrons. That's the point. In a Bohr diagram, it is very easy to imagine how carbon can do this. Same thing with the Lewis diagram. The electrons, the 4 valence electrons are found in the 4 corners, okay, north, south, east, west. They're all in their own 90-degree domain from each other. So it's really easy to imagine that each of those electrons will find another one and you have a full octet. But if you look at the electron configuration, that's not the case. All right, in the p orbitals, the 2pz is completely empty. Right? How can carbon make 4 bonds with an empty 2p orbital? The 2px and the 2py, sure, yeah, they can find another electron, but are you just going to take 2 electrons from some poor atom just to fill your 2pz? How would that work, right? How can carbon share electrons it doesn't have? So this is where you have orbital hybridization. Okay, so carbon will hybridize their orbitals in order to achieve this. How this works is, well, carbon will promote an electron from the s orbital into the empty p orbital. So instead of having s2p2, you would have s1p3. Okay, and we're not done yet. And then all 4 orbitals with 1 electrons each, they will hybridize to make 4 identical orbitals. All right, let me repeat that. Because s orbitals are different from p orbitals, s orbitals, they have lower energy than p orbitals, and they have a different shape too. They are found in a different place. They actually come together and basically evenly divide all of their energy amongst each other and reshape so that they have the exact same shape and energy. All right, as shown in figure C. You see what I mean? In figure C, you see 4 different lobes. One lobe is one orbital. So you have 4 orbitals in that picture. And these 4 orbitals are sp3 hybrid orbitals. All right, so I'm going to label these. This orbital is sp3. This one is sp3. That one is sp3. And obviously the last one is also sp3. So did I make myself clear? The 4 orbitals came together, did some magic, rearranged their energy so that they're now exactly identical, and they have now 4 identical orbitals. Okay, it is not simply one s orbital with 3 p orbitals together. No, despite the name suggesting sp3, it is not one s and 3 p. It is 4 sp3 orbitals. Okay, so another analogy would be, imagine like humans in real life. Some people are rich, some people are broke. Okay, there is a difference in the distribution of wealth in the world. And so Karl Marx envisioned a system where everything is equally shared. Okay, so if the government could just take money from everybody and evenly distribute that among the population, you achieve total communism. And that's basically what this is. Okay, you take the energies from all of the orbitals, doesn't matter how much you have, you evenly distribute them among the 4 orbitals, they now become sp3 hybrids. Okay, and then you can make chemical bonds. If you have 4 different orbitals available for bonding, and this is, by the way, carbon, we started with the configuration for carbon, and it wouldn't shock you to find out that the angles between these orbitals is 109.5 degrees, exactly as a VSEPR structure would predict. This forms a tetrahedral. Okay? And so hybrid orbitals, therefore, would be a combination of at least 2 different orbitals. If you have 2 or more orbitals that come together and form a brand new orbital, that would be a hybrid orbital. And hybridization is simply the process of making hybrid orbitals. So with the sp3 hybrid, they form a tetrahedron, and carbon is now available to make 4 bonds. Let's say if you bond with 4 hydrogens, well, that's how you get methane. Okay, so like I said before, the sp3 orbitals are all equal in energy and shape. They're indistinguishable from each other. And they will, of course, repel so that they will have the most optimum configuration as far apart from each other as possible, forming 109.5 degree angles with everyone else. So do we have any questions about hybrid orbitals? Okay. Now, there are different kinds of hybrid orbitals, and we're going to learn some of them. BeH2. Okay, imagine beryllium bonding with 2 hydrogens. Now, beryllium has 2 valence electrons, 1s2, 2s2. That's it. So the electron configuration of beryllium is right there in the first row. Beryllium, in this case, is making 2 covalent bonds. How? How can beryllium make 2 covalent bonds when beryllium has a complete empty subshell in the p subshell? There's nothing there. So, well, that's when hybridization comes in. An electron will be promoted from the s into the p, so now have s1, p1. And then those 2 orbitals with the single electron, they will come together and hybridize into sp hybrid orbitals. Okay, again, same energy, same shape. So in the picture on the right, that is not a single p orbital. Okay, a p orbital has 2 lobes, but no, that represents 2 different orbitals, and both of these orbitals will be sp hybrid orbitals. Okay, so that's 2 orbitals, not 1. And because they want to be as far away from each other as possible, they have a 180 degree angle between them. And then you're left with two empty p orbitals that really doesn't do anything. Okay, so this explains why an atom like beryllium can only make two covalent bonds. It is unable to complete the octet because you would have empty p orbitals, you have no electrons to share, and you can't just rip two electrons from other atoms. Okay, so beryllium is content with 4 valence electrons for this reason. So this is known as sp hybridization. Why is it called sp? Because one s and one p comes together, so sp. Okay, let's move on to the next type. If you have boron instead of beryllium, well, boron has 3 valence electrons, so it's 2s2, 2p1. And boron, we learned, can make 3 covalent bonds, so BCl3, how's that possible? Well, again, same thing. The s electron jumps into the empty p orbital in the second p subshell. So instead you have s1 and p2. And all those orbitals with the single electron, they will hybridize together to make an sp2 hybrid. Why is it called sp2? Because there's one s and two p's. Okay. Again, you redistribute the energy so that they're exactly the same with the exact same shape, and they will spread out as much as they can, forming 120 angles from each other. So in the picture, you have 3 orbitals of sp2. Okay, and this will form trigonal planar molecular geometry. So this is known as sp2 hybridization. In sp2 hybridization, you have one empty p orbital that didn't hybridize. And this is the reason why boron can make a maximum of 3 covalent bonds, not 4. Because it would have an empty p orbital without an electron, so it would be unable to make another covalent bond. So that's why you have this exception. All right, so did I make myself clear? The next type we've already seen. Let's just review that. sp3 hybrid orbitals. Well, carbon is able to make 4 bonds, so s2p2. So what happens in carbon is the s orbital donates an electron to the p orbital, so now you have 1 each. All of them will hybridize together to make sp3 hybrids. You don't have any empty p orbitals because you used all of them. So 4 identical sp3 orbitals will then be created. Okay, same energy, same shape, with a bond angle of 109.5 degrees, forming tetrahedral structure. So that's how you get methane. So orbital hybridization, they explain the Vesper structures. Okay, so Vesper structure do accurately predict the shape because hybridization occurs to give you that shape. All right, so let's look at some examples and how we can use that to answer questions. So this example says, BF3, determine the type of hybridization, the molecular structure, and draw the orbital diagram for boron before and after hybridization. All right, so we have BF3, right? So you have to realize boron is making 3 bonds, and all of those bonds are with fluorine atoms. So it helps if you can draw the Lewis diagram first. So you see that boron is making 3 bonds, so how many orbitals do you need to hybridize? Well, 3, because you have 3 bonds. You see what I mean? They should be the same. So to make 3 hybrid orbitals, here's boron, you need to create sp2 hybrid orbitals. Okay, 1s and 2p, that makes 3. So you hybridize this by moving the s electron into one of the 2p's. But we're not done. We then need to hybridize them to be the same energy and same shape. So now you have 3 sp2 hybrid orbitals with 1 empty p orbital that is unhybridized. So now boron is ready to make 3 bonds. Okay, so that is the orbital diagram for boron before and after hybridization. The molecular structure and the type of hybridization, well, because you have one S and two P, this is sp2 hybridization for boron. And the structure will be trigonoplanar. Because you have 3 bonds and no lone pairs, you must be a triangle with a 120-degree angle. It will look something like that, okay, BF3. Boron in the middle with sp2 hybrid orbitals, and there's 3 of them. They will overlap with the p orbitals in fluorine, and that will be the structure if you want to draw out the orbital diagram of the structure. Okay, questions about this example? No? Okay. Let's look at the next example then. So you would have example 2, NH3. So you have ammonia this time. So determine the type of hybridization, the molecular structure, and draw the orbital diagram. So this one is a little bit harder than the previous one. You have to consider what does the nitrogen have to do? The nitrogen is making 3 bonds with hydrogen, but is that it though? No, the nitrogen also has a lone pair. All right, so you have to realize nitrogen makes 3 bonds with hydrogen. So therefore, it will still need 3 bonding orbitals. Okay, that doesn't change from the previous example, but also there's a lone pair. So that's the configuration for nitrogen. How would you hybridize this? You don't really need to promote that electron. So all you have to do is hybridize all of them because the lone pair also takes up space. The lone pair also needs to be in the electron configuration in the final structure. NH3 is also a tetrahedral if you count the lone pair. All right, so you can't just form the bond without the 2s. So this is an sp3 hybridization. It's just that one of that sp3 orbital already has 2 electrons, so it doesn't need to make a bond. All right, so that's what you get. And sp3 for nitrogen, the structure will be trigonopyramidal. And here's the Lewis diagram. Oh, sorry, here's the Vesper diagram. Trigonopyramidal because the lone pairs, we can't see that, so it looks to us like a pyramid. But still, you have to know that this would be a tetrahedral if you can see the lone pair. So that means lone pairs also count. Here's a trick. To determine the hybridization of any atom, just consider the atom's steric number. How many things are attached to that atom? So in this case, nitrogen has 3 hydrogens attached and 1 pair of electrons for a total of 4 things attached to the nitrogen, meaning that you need 4 orbitals to contain all of them. So therefore, sp3. Okay, 3 plus 1 is 4. Is that clear? I'm not getting questions today. That's either very good or very bad.
What is like this sp3 different than the one just with 1 arrows?
Or how is sp3 different from?
From like CH4, like the sp3.
Okay, so they're both sp3, right?
Yeah.
With CH4, you have 4 sp3 orbitals, each with 1 electrons inside. But with this sp3, with the nitrogen, you still have 4 sp3 orbitals. That doesn't change, but only 3 of them has 1 electron. 1 of them already has 2 electrons. So instead of making a bond to get 2 electrons, it doesn't need to. It already got a partner, so that's a lone pair.
But it still counts as a sp3.
Yeah, that's still sp3 because you still need an orbital to hold those lone pairs. You see what I mean? So you still need to hybridize those.
Okay. Thank you.
You good?
Yeah.
Okay, and nothing changes if you have, like, say, water, because you have 2 lone pairs. Same thing, still sp3 because you need 4 orbitals. Okay. What about double bonds and triple bonds? right? How does that change? Well, if you consider these three structures, C2H6, C2H4, and C2H2, if you draw their Lewis diagrams, you're going to get something like that. Don't mind the bond angles. The bond angles are not right, but we don't care about the bond angles right now. In the first one, C2H6, you have all single bonds. Okay, every bond has 2 electrons shared, but C2H4 has a double bond between the carbons, 4 electrons are shared, and C2H2, there's a triple bond. How do we overlap the orbitals to get the triple bonds? Well, then we have to invoke 2 different types of bonds. The first one is end-to-end overlap. Okay, so you have 2 orbitals, they overlap end-to-end. Okay, does that make sense? That would be everything we've learned so far, and those are called sigma bonds. Okay, sigma bonds, end-to-end overlap, that's quite simple. The other type of orbital overlap will be side to side, the Ariana Grande style, like this. If they overlap side to side, we call these pi bonds. Okay, so you either have sigma, end-to-end, or side to side pi bonds. Let me show you some examples to illustrate this. So first of all, sigma bond. If you have 2 s orbitals, that's easy. Just come together. There you go. That's a sigma bond right there. If you have 2 p orbitals, nothing changes. Just come together. The overlap orbital gets proportionally bigger, and the non-overlap, the other lobe, gets smaller. So most electrons are found in between. Still, that's a sigma bond because you came head on. Okay. For C, you can have 2 hybrid orbitals, 2 sp3s overlapping. Again, nothing changes, sigma bond, because this end-to-end overlap, the overlap part gets bigger, the non-overlap lobes become smaller. So you have sigma bonds like this. However, pi bonds are created from non-hybridized orbitals. Okay, these orbitals goes up and down, and these 2 orbitals happen to be parallel to each other. So they can't do this. They can't go end to end. So they must go side to side. And the side to side overlap generates pi bonds. And when they overlap, you have electron density near the top of the overlap and the bottom, but in the middle, they cancel out. There's nothing in the middle. So that's the hybrid orbital after they overlap, pi style. So that's a pi bond. Now, why would you ever have an orientation like that? Well, if you check out the picture to the right, the blue lobes, they represent sp2 orbitals. Okay, so this is an sp2 hybridized orbital, which means you have 1 empty, unhybridized p orbital. Okay, because you have 3 p orbitals, only 2 of them hybridized. Well, I shouldn't stick up that finger. Only 2 of them hybridized. You have 1 left. All right, and that p orbital didn't change. It's still a p orbital. That's why it has 2 lobes, and it just so happens to be situated on the z-axis. That's the 2pz orbital. Nothing's changed about that. All of its friends decided to become sp2. This one remains unchanged. So as a result, this p orbital is perpendicular to the plane of the sp2s. All right, so you have a 90-degree between that plane and this p orbital, and it has 2 lobes because p orbitals have 2 lobes. And if you meet another atom just like that, you would have another p orbital, and they would be parallel to each other, and they will be able to bond with a pi bond. Whereas the other ones, the sp2 hybrid, they will do a sigma bond. All right, so there will be a picture later, but let's look at the electron movements first. So for C2H4, there is a double bond between the carbons. So this is what happens in the electron configuration of those 2 carbons. You have 2s2, 2p2. Okay, that's a carbon. Same thing, you promote an electron to the p, so you have 2s1 and 2p3. So you have 4 orbitals, all with 1 electrons each. The difference starts now. When they hybridize, you have sp2 hybrid. You leave one behind. You only hybridize 3 of them. So the 2pz does not hybridize, it stays normal. Okay? It's like you have 4 people, 3 of them decides to go to the mall, leaving one behind. And that is how you get the extra orbital to make the pi bond. The 2pz has a responsibility to make the pi bond, whereas the sp2 hybrid, they make sigma bonds. All right, and a picture will be something like this. Figure A, you have the sp hybrids. By the way, figure A and figure B can be put together, but it's too messy to have all of them in one picture, so it's separate. So in blue, figure A, you have the sp2s. You can see that there's 3 of them, so 3 orbitals, which makes sense. 2 of them are bonded to hydrogen, and the other one is bonded to another carbon. All right, so you have that shape. Now, if you just bring your attention to the lonely unhybridized 2pz orbital that got left behind, well, that's figure B in yellow. Okay, all of his friends have hybridized in that plane, but the 2pz is perpendicular to everybody else. And because there are 2 carbons, there will be 2 unhybridized 2pz orbitals, and they would be just looking at each other. It's like, hey man, you want to just hang out? So they actually will hang out in the sense that they will overlap side to side and form a pi bond. And figure C is the combination of figure A and figure B after having formed all of those bonds. Now, I really don't understand why the colors are reversed in figure C. Yellow is now sigma bond, and the blue becomes pi bond. Right, so if you count them, there are 5 sigma bonds in here, 1 sigma bond between the 2 carbons, 4 sigma bonds with the 4 hydrogens, and there's only 1 pi bond, and that pi bond exists between the 2 carbon atoms. All right. The pi bond has 2 lobes, one on top, one on the bottom. That's 1 single pi bond. Okay, that's not 2 pi bonds. So the electrons can be found above or below. You have a chance of finding it in either of those locations. So do we have any questions about orbital overlaps and double bonds?
I don't understand why the PZ doesn't become a sigma bond.
Right. So why can't the 2pz just be a sigma bond like everybody else? Imagine if that actually did happen. You would have sp3 hybridization. You would have a tetrahedral. Okay, and you can't form an additional bond with the tetrahedral. The angles won't allow it. So that means you have a mission. You have to stay behind because you need to form a new type of bond, the pi bond. So that's why you don't hybridize. You can only form a pi bond if you're perpendicular. If you hybridize, it would be a tetrahedral. The angle wouldn't check out, so you wouldn't be able to overlap that way. You see what I mean? The sp hybrids, they only do sigma bonds, and we only need 3 sigma bonds per carbon, so I only need 3 orbitals, so that's why you don't hybridize all of them.
Okay.
Okay, another question?
Is there only 1 pi bond in graph C?
Yeah, in C, there's only 1 pi bond. Despite having 2 lobes for the blue, only 1 pi bond. Okay, so a double bond consists of 1 sigma and 1 pi bond. Does that make sense?
Yeah.
All right, so let's look at triple bonds now. So again, I said double bonds contain 1 sigma and 1 pi. A triple bond will contain a sigma and 2 pi bonds. So 3 bonds, triple bond. How would a triple bond work? Well, consider carbon again. If you look at the diagram on the right, 2s2, 2p2. Okay, same story. You promote one of the s's into the p. You have 2s1, 2p3. You could, of course, hybridize all of them and make an sp3 hybrid. That's just methane. But if you want to make a triple bond, you can only hybridize 2 of those, the sp hybrid. Okay, why? Because if you make a triple bond, that means you need to make one sigma bond with the other carbon and one sigma bond with something else. All right, and 2 pi bonds will complete the triple bond between the 2 carbons. So again, triple bond is 1 sigma and 2 pi, so you need a sigma for the carbon, and you need a sigma for the other thing. So that's why it's sp, just 2 things. You need to leave behind 2 normal p orbitals because you need them to make 2 pi bonds. And if you look at the diagram on the top, that's what happens. In blue, you actually have 2 orbitals, 2 sp orbitals, okay? In yellow, you have just 2 p orbitals. Because a p orbital has 2 lobes. I know there are 4 lobes, but that's actually just 2 orbitals. Okay, one is vertical, one of them is sideways. You see what I mean? You see the difference here? A p orbital has 2 lobes, but sp only has 1 lobe. So there are 2 sp orbitals and 2 p orbitals. And those p orbitals are able to make pi bonds at perpendicular 90-degree angles, okay, from each other. All right, does that make sense? All right, so let's actually look at a picture of a triple bond. Well, this is going to get a little bit confusing. Figure A, if you just look at figure A, that is just the normal sigma bonds. Right, the 2 carbons will bond with each other normally. You overlap end to end, and there you have it. And then the other sigma bond will have a hydrogen on it, so you overlap with the 1s of the hydrogen. That's fairly simple. If you want to look at the unhybridized p orbitals, you go to figure B. Figure B has the p orbitals in a cross, 90 degrees from each other. Because there are 2 carbon atoms, you have 2 of this. And they will exactly match up, and they will overlap, forming figure C. If you combine all of these together, they overlap to figure C. And I don't know why the colors are reversed. Actually, the colors are not reversed. It's just the pi bonds are in blue now. You can see that there are 4 tube-like things that are blue. Those are the pi bonds. Across from each other, you have 1 set of pi bond. And perpendicular to that, 90 degrees across from each other, you have the second set of pi bonds. So for a total of 2 pi bonds, and in the middle you have the sigma bond, and that's a triple bond. Does that make sense? All of the p orbitals are 90 degrees from each other, and there are 2 unhybridized p orbitals. They each make a pi bond, so 2 pi bonds, along with a sigma bond that is made between the 2 carbons, that forms the triple bond. No questions. All right. Obviously, I'm not going to make you draw that. That's just crazy. It's not our class. You just have to understand the concept. So, example 3. H2CO. Determine the type of hybridization of carbon, the molecular structure, and draw the orbital diagram for carbon before and after the hybridization. All right, I'm going to show you how to do this one. I'll ask you to do the next one on your own. First of all, you have to figure out what types of bonds is the carbon making, and how many things are sticking out of that carbon. And to do that, you must draw the Lewis diagram. But once you do, you're going to realize that the carbon makes 2 sigma bonds with the hydrogen and a double bond with the oxygen, so a sigma and a pi with the oxygen. So that's a total of 3 sigmas and 1 pi. And in order to get 3 sigmas and 1 pi, well, you hybridize, you move the s electron into the p. You must hybridize 3 out of the 4 orbitals to have sp2 hybridization, because in the sp2 you will have 3 orbitals available for sigma, and the unhybridized orbital will be available for the pi bond. Okay, so that will be the orbital diagram of carbon. And what would be the molecular structure? You have to think about how many things are sticking out of the carbon. You have 2 hydrogens and one oxygen, despite having a double bond, that is still counts as one thing. So that means you have three things sticking out of your carbon. So a short way of remembering, just count the sigma bonds. You have three sigma bonds, so three things sticking out. No lone pairs, so that is sp2 hybridization, and this would be trigonal planar. Okay, and that will be the structure of SCH4U. Okay, so did I make myself clear? How do you determine what type of hybridization you do? That depends on your steric number. How many things are sticking out of your carbon? In this case, three things stick out, so sp2, because 1 plus 2 is 3. And if you do sp2, naturally you have one orbital left. That's your pi. All right, so if you don't have any questions, work on the next example. It is the same molecule, except it's, instead of carbon, we're going to look at this from the oxygen's perspective. Figure out the hybridization of the oxygen. Okay, you don't need to figure out the molecular structure because it's silly to talk about the structure from not a central atom. So just figure out the type of hybridization of oxygen and draw the orbital diagram. So try this on your own. I'm going to give you like 1 to 2 minutes, and then I'll take this up. All right, I'm going to show you how to do this then. Same thing, except with oxygen now. You have to first figure out what bonds is the oxygen atom making. Okay, so the oxygen is making a double bond with the carbon. And that's when no other bonds are made. So 1 sigma and 1 pi. Okay, so how would you hybridize that? This is oxygen. All right, 6 valence electrons with 4 orbitals in the peak. You would then hybridize it like this. Now, why? Because you just need 1 sigma bond with the carbon, and the other one is a pi bond. So all you have to do is just hybridize 3 of them and leave 1 remaining for the pi bond. All right, and also oxygen has 2 lone pairs. And those 2 lone pairs also need to occupy an orbital, and so they also need to be hybridized, meaning that you need sp2 hybridization. Okay, in your sp2, 2 of them are already full. That's a lone pair. One of them has only 1 electron, while you're looking for another one with a sigma bond. The one left behind, your unhybridized p, that's your pi bond with the carbon. So that would be your orbital diagram. And the hybridization will be sp2. Okay, if you're confused as to how can I figure that out, here's a very simple way of doing this. Whenever I ask you for the hybridization of any atom in a compound, just ask yourself the question, what is that atom attached to? This oxygen is attached to the carbon, and it has 2 lone pairs. So that's 3 things in total. That would be sp2 because you need 3 orbitals for that. You see what I mean?
Does it like always work?
It always works.
Okay.
It depends on how many things you have attached to that atom. If you have 4 things attached, that's sp3 because you will need 4 orbitals, right? If you have if you have 1 thing attached, I wouldn't ask you that question. If you have 2 things attached to it, that will be sp hybrid because you need 2 orbitals. If you have 3 things attached, you have sp2. 4 things, sp3. If you have 5 things attached, like for example, PCl5, that guy has 5 things attached to the phosphorus. We learned how to draw that with the Lewis diagram lesson. What kind of hybridization would you have? Well, you need 5 orbitals. So 1 s, 3 p's, that's the maximum of number of p's you can get. So now you have 4. You're still missing 1. Where do you get the last orbital from? Anybody?
Another s.
Not from the s. You already took it from the s. Remember what we learned, expanded valences in that lesson? I said that only elements with n equals to 3 and greater can have expanded valences because they have access to something the second row doesn't. What is that something?
More than 8 electrons in the...
Yeah, but how are they getting more than 8 electrons? Where are they fitting those electrons? They got to stash them somewhere. They all have access to extra orbitals because in the third level, you have d orbitals. In the second level, you don't have d orbitals. So the extra electrons are stashed in the d orbitals. So if you have something like PCl5, the hybridization on the phosphorus will be sp3d. They add up to a total of 5. You see what I mean? Similarly, if you have, let's say, SCL6, you have 6 things attached to the sulfur. That would be sp3 what?
D2.
D2. Okay, you just need to add them up so that you have enough orbitals to contain everything. That is the easiest way of remembering. Just ask yourself the question, how many things are sticking out of that atom? And that should tell you what kind of hybridization that atom needs. So that never fails. All right, so example 5. This one is a triple bond, C2H2. So determine the hybridization of carbon, the molecular structure, and draw the orbital diagram for carbon before and after. So attempt this one. I'll give you a couple of minutes. I hope this one, it will be a little bit easier for you. All right, for this one, you have to know that the carbon has a triple bond with the other carbon and a single bond with the hydrogen. So 2 sigmas, one for hydrogen, one for carbon, and 2 pi's to make the triple bond. To hybridize for that, well, first of all, you need to move the electron to the p. And then to hybridize for a triple bond, you have sp hybridization. You need to leave open 2 of the p orbitals because you need 2 pi bonds. All right, so that's what you have to do. So therefore, this is sp hybridization. Okay, so to do this quickly, the carbon has 2 things sticking out. 1 carbon and 1 hydrogen, that's it. So I need sp. And the structure is linear. It looks like that. It's straight up a straight line because you have to be 180 degrees from each other. Okay, so we're good so far.
How does it make 2 pi bonds with carbon?
Well, it makes 2 pi bonds because a triple bond has 1 sigma and 2 pi's. If you have 1 pi bond, that's a double bond because sigma and pi is double. You see what I mean?
Yeah.
All right, so here is a practice page. In this page, you have to draw the Lewis diagram, and then all you have to do is figure out the hybridization of the central atom. All right, so I'm going to give you like 2 minutes on this, and then I'll take it up, and we'll end it here. All right, so first of all, you have to draw this. So water, you should make sure that this is bent. In the next lesson, we're going to learn intermolecular forces and polarity. You need to make sure that water is bent because if you draw this as a linear molecule, you're going to think that this is non-polar, which is not the case. So bend the water. What type of hybridization?
sp2? No, sp3. Sorry.
sp3. Okay, because the oxygen has 4 different things on it, 2 lone pairs and 2 bonds. So 4 different things, that's AX2E2, so a total steric of 4. Now, methane is probably the easiest one here. The carbon has got 4 bonds, so what is it? Anyone?
sp3.
sp3. Okay, 4 bonds, so 3 plus 1, 4. Ammonia, nitrogen's got 3 bonds and a lone pair, so that makes a total of 4. So the answer will still be sp3. Nothing changes. Okay, so you can see that you can have no lone pairs, one lone pair, or two lone pairs. It doesn't matter as long as you have 4 things, you're sp3. Carbon dioxide is a linear molecule with 2 double bonds on the carbon. What type of hybridization do you have on the carbon?
SP.
Just sp or something else?
SP.
Just sp. Okay. It has 2 things sticking out from the carbon. So you need 2 orbitals for that, 2 sigma bonds, so sp. Right, the other 2 are in the pi bond. There are 2 pi bonds, 1 with each oxygen. Okay, nitrogen, there's a triple bond there. So the hybridization is
SP.
sp. Again, the nitrogen has 2 things sticking out of it. One is the lone pair, and the other is the other nitrogen. So sp. And the last one, B2F4, it looks like that. The boron has a hybridization of
SP2.
sp2 because it's got 3 bonds, 2 with F and 1 with the other B, so you need 3 orbitals for that, so sp2. All right, so I hope you guys see the pattern here, and you guys will be able to recognize the hybridization of various atoms if you draw the structure. All right, so do we have any questions before we end it? So we learned about hybrid orbitals, sp, sp2, sp3. We learned about sigma versus pi bonds and how they can overlap. Questions, folks? Okay. So I'm going to end the video here.